Welcome! In this session we will talk about linked data and semantic web standards. The basic set of semantic web standards was defined by the World Wide Web Consortium. They consist of a flexible data model, schema and ontology languages for describing concepts and relationships, data serialization formats, and a query language. We will now get to know each of those standards in a little more detail. Semantic web technologies are a set of tools and standards around the topic of knowledge exchange and management. While semantic web technologies were originally conceived to improve the exchange and management of knowledge on the World Wide Web, the tools and standards that originated from this initiative are just as beneficial for being used offline or in internal networks. The RDF data model forms the basis of all semantic web technologies. RDF stands for Resource Description Framework. The basic idea of the RDF data model is to describe resources with statements. A statement consists of three elements: subject, predicate, and object. Because every statement consists of three elements, statements are also called triples. With the subject-predicate-object structure, triples are very close to natural language. As an example, we could take the statement Anne likes apples. Anne would be the subject, likes the predicate, and apples the object. In this statement, Anne would be a resource in our dataset. With the statement, we describe our resource Anne. We can add many more statements to describe our resource Anne in more detail. For example, we can say that Anne dislikes pears, or that Anne teaches linguistics. We can also extend our dataset to include apples and pears as resources that we can also describe. We can say that apples are fruit and that pears are also fruit. This data structure allows for several things. First, it allows us to build long chains and networks of interconnected statements. This is why it is also called linked data. The RDF data model is based on the idea of linking resources in its very core. Secondly, it allows us to query, filter, and explore the data based on both the triple data structure and also based on the connections between individual statements. The second major cornerstone of RDF data is the requirement that each resource as well as links between resources are uniquely identifiable. Each resource and each predicate is assigned a uniform resource identifier, a URI. This URI can be any ID that is unique. Because of its origins in the web community, it is a de facto standard that web URLs are used as URIs. This has the advantage that it is possible to host information about a resource in that web location that is specified by the URL. This means that URIs can be resolved with a web browser, and it is possible to retrieve information about a resource in this way. Using resolvable URLs as URIs is not a requirement of RDF as such, but it has become best practice. If we go back to our example about Anne, we would now like to assign Anne a URI. The first statement we would make about Anne would look like this. First, we have the URI of our Anne resource. Second, we have a URI for the predicate. In this case, it is a predicate that tells us that it will be followed by a label, or a name. The object of our statement would then be Anne's name as a simple string. This statement tells us that the subject URI has the name Anne. If we now want to say that Anne likes apples, we would add a second triple. Again, we would start with the URI for our Anne resource. We would then add a URI for the likes predicate. This URI can be defined in whatever way we want. The only requirement is that it is unique within the dataset. The object of our second triple would be a URI for the apple resource. So now Anne has a URI Apples have a URI, even the predicates like and has a label or name have URIs. But the string an, the label itself, does not. In RDF, we try to assign unique identifiers to as many elements as possible. As soon as we have a URI, we can describe an element, that is, we can say something about it. We cannot say anything about the string an, because we cannot uniquely identify it in a second statement. We could never be sure that the string an used in one statement is the same as the string an used in another. By assigning URIs, we try to overcome the inherent ambiguity of language. Every element is defined once, and when we reuse it, we use the same URI to clarify that it is the same element. Only elements that are used only once are kept as strings, such as an, the label of our resource. Besides the triple data structure and the requirement for unique resource identifiers, the RDF standard also defines some elements that can be used in your data. As an example, the RDF standard also defines a type predicate. The RDF type is one of the elements that you will find in almost every RDF file, because it is often very useful to assign a type to a resource. If we go back to our example, we could say that an has the RDF type person. This statement says that an is a person. To summarize, the RDF data model is based on three important definitions. First, the definition of the triple data structure, subject, predicate, object. Second, the requirement of a uniform resource identifier for each RDF resource. And third, the definition of some basic elements that can be used to describe RDF resources. There are a number of other standards that define elements that can be used to describe resources. They don't only define predicates, but also classes, that is, types of resources that you can assign to resources in your dataset. These standards are called ontologies. The RDF standard contains a very basic ontology with a few classes and predicates. An extension of the RDF ontology is the RDFS ontology, the Resource Description Framework schema. RDFS is a kind of meta-ontology. It is an ontology that defines elements that are used by other ontologies. For example, RDF class is one of the classes in the RDFS ontology. Other ontologies assign this class to their classes to specify that they are classes. Another standard ontology that is also published by the World Wide Web Consortium is the SKOS ontology, the Simple Knowledge Organization System. We have already used an element from the SKOS ontology in our previous example. The SKOS preferred label is a predicate defined in the SKOS ontology. The SKOS ontology provides a basic set of classes and properties with which you can describe resources already in quite some detail. The SKOS ontology is very widely used, and it often forms the basis of data models that are extended with other elements as is needed. Other widely used ontology elements come from the OWL ontology. OWL stands for Web Ontology Language, and it is really a language that can be used to write ontologies. But within that language, there are also some defined elements that can be used directly to describe resources and links between resources. Beyond the provision of some ontology elements, with OWL it is possible to express logic that can be used to check data consistency and support inference of information from existing information. The RDF data model and standard ontologies alone are not sufficient to be able to create and manipulate, and in particular to exchange RDF data. To do this, we need yet another set of standards that define how RDF data can be written down. We need serialization formats for RDF data. A serialization format is a definition of how the elements that RDF data consists of can be put into a file and read again by another application. Examples for common serialization formats are turtle, ntriples, nquads, JSON-LD, N3 or notation 3, RDF XML, trig, and tricks. Let's take a look at some of those serialization formats. Ntriples is the simplest and easiest to understand serialization format. In an ntriple file, every statement has its own line, and every line always only contains one statement. For our little example about Anne and apples, an ntriples file could look like this. We can see that a few things look different here than when we wrote down triples before. First of all, you can see that all URIs are placed inside angular brackets. The angular brackets are standard markers for URIs. The machine will know that whatever is between those angular brackets is a URI. Similarly, strings are demarcated by double quotes. The label of the Anne and Apple resources are demarcated by double quotes. We can also see that every line ends with a dot. This dot demarcates the end of a statement. Another popular serialization format is the turtle format. Here the data is represented much more densely. Let's see if we can find our triples. Here we have a subject, here we have the predicates, and here we have the objects. In contrast to the ntriple format, the subject is not repeated. We have each subject once, and then a list of predicates and objects that are associated with that subject. As long as there is still information to follow about the same subject, the lines end with a semicolon. Only when one subject is described completely, we have the dot. In this case, the dot demarcates the end of a series of statements that are tied to the same subject. Another thing we notice is that the file starts with prefixes. Using prefixes makes the resulting file smaller and easier to read. You can think of the prefix as a variable. You say that with RDF:, you really mean http://www.w3.org/1999/02/22-rdf-syntax-ns#. In the file, you can then use RDF: and add only the very last part of the URI, e.g. type, so that RDF:type becomes equivalent to the full URI of http://www.w3.org/1999/02/22-rdf-syntax-ns# type. The last serialization format I would like to look at is the XML RDF serialization format. You probably have heard of XML before. It is a common serialization format used for many different types of data. Here it already becomes a little more difficult to find our triples. Here we have the subjects, here we have the predicates, and here we have the objects. As you can see, there are also prefixes. Other than that, the use of angular brackets and quotes is different, and the overall look of the file is also quite different than the other serialization formats we have seen. To sum up, there are different serialization formats for RDF data that can look quite different. But they all contain RDF data with a subject-predicate-object data structure, and they all can be read by applications that know the rules of the serialization format. Now that we have heard so much about how we can describe and encode information in RDF format, I would also like to talk about how this data can be retrieved again once you store it in RDF format. Together with the RDF data model, the World Wide Web Consortium defined a standardized query language for RDF data, SPARQL. SPARQL is a reverse acronym for SPARQL Protocol and RDF Query Language. SPARQL offers unique advantages for querying data that are closely tied to the triple data structure. For example, you can retrieve data by asking for all the objects that follow a specific predicate, or by asking for all subjects that have a certain RDF type. You can also use the links between statements for querying. This allows to pack a lot of logic into a very simple query. As an example, we can ask for all fruit that Anne likes, which will be very easy to answer with a simple Sparkle query, despite the fact that Anne and fruit are never mentioned together in one statement. This is because the data is linked. There is a clear connection between Anne and fruit that we can use for querying. Let's recap what we have heard in this session. We have talked about RDF, the Resource Description Framework, a standard published by the World Wide Web Consortium. In RDF, all information is expressed in the form of triple statements. A triple statement consists of a subject, a predicate, and an object. Most elements in RDF are assigned URIs, Uniform Resource Identifiers. It is best practice to use resolvable URLs as URIs. We have also heard about standard ontologies that define elements that can be used to describe resources. RDF comes with a small, very basic ontology. An extension of RDF is the RDFS ontology, the RDF schema. Other common ontologies are SCOS and OWL, which is really a language for defining ontologies more than an ontology itself. We have also heard about serialization formats of RDF data, and about Sparkle, the standard query language for RDF data. There is a dedicated learning session about the Sparkle query language later in this module, where you will hear more about the use of Sparkle to query RDF data. Stay tuned!